Assalamualaikum and good morning, everyone.
Good morning, sir.
Good morning, sir.
Waalaikumsalam.
Alright, semangat terus. Okay, so today we will continue with our lecture. Okay, so on Monday, last Monday, we have learned about the introduction about basic control system. So now we will move to chapter 2 and lecture 2A, and we will go into to model the dynamic of a system so that we can later on analyze the system and then develop the control system of that system. Okay. And in lecture 2A, we are going to look at one of the most important aspect of automatic control, which is the transfer function. So after completing this lecture, students will be able to perform Laplace transform and inverse Laplace transform. So I think you have probably learned Laplace transform in ODE or maybe Fourier transform. They are basically the same thing, but with slight difference. Okay. And then we are also going to learn about how to use partial fraction expansion, and then we will learn also on how to convert a differential equation or ODE into transfer function. Okay, so Laplace transform is basically a technique that transforms a time domain function into a frequency domain. So time domain function is a function that changes with time. For example, like maybe y equals t squared, for example, okay? Like y equals t squared. So y will depend on time. Okay? Whenever time change, then y also change. But sometimes it's easier to analyze an equation if we can convert it into frequency domain. So we know that frequency f is equals to 1 over period. Okay, so this is like the general relationship between frequency and time. So the purpose of Laplace transform is to convert a function of time into a function of frequency. Okay, let's say g, function g. Okay, so the purpose of Laplace transform is it can be used to solve ODE. Okay, so ODE that you have learned before, maybe in ODE subject. Sometimes you learn on how to solve ODE using manual calculation. Okay, and sometimes you need to use integration. But Laplace transform basically also integration, but it's already you already have a table, a list of function that you can convert straight away into frequency domain. Okay, so you don't need to use integration, but you can straight away refer to the table. And Laplace transform converts a differential equation into algebraic form, meaning that differential equation is an equation that has like dy dt, for example, which is requires you to use integration to solve the equation. But when you use Laplace transform, then the equation becomes in the form of algebra, okay, like a plus b, for example, okay, which is simpler to solve. Thus, this Laplace transform avoid the use of differentiation or integration. So the definition of Laplace transform. So let's say if you have a function of time, ft, function of time. So you want to convert it into function of frequency. So in this subject, in automatic control, we use S to represent frequency, okay? Later on in next lectures, like maybe chapter 3, we will see what is S represent. But for now, I want you to take that S as a frequency, okay? So when you apply Laplace transform, so L represent Laplace transform. So Laplace transform of F, of function F, you will get a function of in the form of frequency. So usually we use F, small f, as a function of time, and big F, a function of frequency. Okay. And the formula of Laplace transform is basically this integration of f of t, times e to the power of negative st dt. Okay, so basically Laplace transform is an integration of ft, but you multiply with exponential of negative st.
Doctor,
Yes, sorry.
so doctor, what is mean by zero negative? Is it negative infinity?
Zero negative means if you look at graph, so this is zero. So it's like starting just before before zero. Okay, but don't worry about this definition, because later on we will see a table that lists all the conversion of some function into frequency domain using Laplace transform. But this is just a general definition of Laplace transform, meaning that if you use Laplace transform without table, then you need to use this integration. But most of the time, you will use table. I mean, all the time in this subject, you will use table to convert time domain function into frequency domain function. Okay, so we can also transform from frequency to time domain function. So this is frequency. We want to convert back into time domain. So we use inverse Laplace transform. So inverse Laplace transform is represented by L power of -1, meaning the inverse of Laplace transform. And then this is the formula. Okay, so don't worry about the formula. This is just to define, okay, what is Laplace transform. So when you convert from frequency to time, then there will be this function. You need to multiply this function ut. So basically ut is a function that the meaning of ut is basically a function that has value 1 when time is bigger than 0, or meaning positive time. And then u is 0 when the time is negative. Okay. So the meaning of u is basically it assumes that the time is always positive, meaning that negative time, for negative time, then the function is 0, or the value of that function is 0. So maybe later, maybe in tutorial, you will see ut, okay, or maybe in example later on. So ut is basically a function that is equals 1 when time is positive, okay. So when time is not positive, then it's equal 0. Okay, so this is the table that I talked about. So we don't need to use the integration definition of Laplace transform, because that is very traditional. Okay, so people already list down all the basic transformation of Laplace transform. So for example, if you have a del function, del t, so del function is a function that is when time is 0, it's equals 1. And then for time not equal 0, then the function equals 0. So it's a function that only have value at time equals 0. Okay. Okay, so del function is seldom, very rare to use in control system. So if you convert del t into frequency domain, it is equals 1. Okay. So the function ut that I explained just now, which has value equals 1 when time is positive. So if you convert this into frequency domain, then you will get 1 over s. Let's say if you have time t times ut. So if you convert into frequency domain, you have 1 over s squared. And what happens if the time here is has a power of n? So you have in frequency domain, it is equals n factorial. Okay, so this is factorial, bukan terkejut So this is factorial, and factorial divided by s to the power of n plus 1. Okay, so the first three are the most common. Okay, the most common definition or things that you need to somehow ada dalam kepala lah. Okay, whenever you see an equation, you know already that t times ut it's 1 over s squared. Okay, and there are other definitions. So let's say if you have exponential power of negative at times ut, that in frequency domain it becomes 1 over s plus a. Okay, so it becomes it takes this a value here. So if you have a sine function, sine omega t, so in frequency domain it becomes omega divided by s squared plus omega squared. And if you have a cosine function, cosine omega t, then it becomes s divided by s squared plus omega squared. Okay, so these three are kind of uncommon lah, macam rare sikit. Okay, but I think if your exam is face to face, this table will be provided. Okay. Okay, so just now we have a look at the table of conversion of Laplace transform for common functions. Now we look at some theorem related to Laplace transform. Okay, so the first one is the definition that I explained just now. From frequency domain, from time domain to frequency domain, then you need to use integration definition. So this is the general definition. Okay. So we already have the table, so you don't need to memorize the integration. So let's say if you have a function ft multiplied with some coefficient, some constant. So let's say if you have k times t ut, for example. So what happened to this k? So if you convert this to frequency, you will get 1 over s plus 1. Okay. S squared, sorry. Okay, so s squared. So how to consider the k here? So in Laplace transform, you have linearity theorem. So if you have coefficient k, you just multiply k with the transformation into frequency domain. Okay, so you transform the function and just multiply k, so it becomes k over s squared. And let's say if you have two functions that are added, let's say function 1 plus function 2, if you use Laplace transform, then it becomes frequency function 1 plus frequency function 2. Okay, so you just convert each of the function separately depending on addition or subtraction. And if your function f is multiplied with an exponent negative at. Then in frequency domain, you just need to add the value of a here to s, okay, to the frequency. And let's say if you have your time shift, okay. So let's say your time is shifted by a time t. Then in frequency domain, you just multiply with exponent of negative st of that shift, of the time shift. Okay, so these two are also uncommon, okay. Usually the first two here are the most common, as well as the number 6 here, also uncommon. Okay, so let's say if your time is has a scaling, has a scale, then in frequency domain, you just divide by the scale 1 over a, and then the frequency also divided by the scale. Okay, so number 7 is important, especially in our class, automatic control. So let's say if you have differentiation of time function f, let's say df dt, then in frequency domain, it becomes s times fs minus f0 negative. Okay, so this is depending on the initial condition of ODE. But most of the time, the initial condition given to you is at time 0, then the value of f equals 0. So most of the time is this, okay? So usually we ignore this term here. So what happens is that if you have differentiation of f over time in frequency domain, you just multiply by s. Okay, so df dt, it becomes sf. Sometimes we use f dot to represent df dt, or sometimes f prime, okay, to represent df dt. So if you let's say find f prime or f dot, then in frequency domain it becomes s times f big F. Okay. And then if you have double differentiation, d squared f dt squared, then it becomes s squared f. And this part here, usually we assume equals 0. Okay. I think so far there is no example or question that requires you to use this. Okay. Usually we assume this is 0. Okay. And let's say if you have differentiation many times, like n times. So if you convert in frequency domain, it becomes s power of n times f. Okay, so this is the general definition of the differentiation theorem. Okay. Okay, the last three here are not important. Okay, it is there because the lecture notes is taken from somewhere. Okay. Tak patut delete je lah, tapi itulah. Okay, so a few things that you need to remember is theorem 2 and 3, linearity theorem, and also differentiation theorem. Okay, because we are going to encounter this many times in this course. Okay. Okay, so let's look at an example on how to perform Laplace transform. So in this example, we use the traditional method using integral approach. So let's say if you have an ODE, dy over dt equals a with 0 initial condition. So traditionally, you will use integration to find y, okay? So y equals integration of a dt. So this, if you integrate this, becomes at. Okay, so becomes at. And then you substitute at time t minus at time 0. So you get at. So y equals at if you use integral approach to solve an ODE, okay? So it's easier in this case, at least, to use integration to solve ODE. So let's say if you use Laplace transform to solve the same ODE. So let's say the same ODE, dy dt equals a. So you use Laplace transform. You use the table that I explained just now. So you take Laplace transform of both sides. Okay, dy dt, Laplace transform, and then a, Laplace transform of a. So dy dt, if you take Laplace transform, we use the differentiation theorem. So you get s times big Y. Okay, from small y becomes big Y. And then Laplace transform of a constant A. So in the case of constant, we assume that this constant is always positive when time is positive. So basically, it's a times the function ut. But most of the time, the function ut is not written. Okay, dia tak tulis function ut. So what happens is that in frequency domain, it just take the Laplace transform of ut, which is a over s. Okay, so sy equals a over s, and then rearrange to get y equals a over s squared. And then to get y, to get the small y, we need to use inverse Laplace transform. Okay, so we perform inverse Laplace transform. Okay, so inverse Laplace transform of y, big Y, you get small y. Inverse Laplace transform of a over s squared, you get a, so times t ut. Okay, so you need to look at the definition from the table. So 1 over s squared is equals t times ut. And then rearrange. So you get y equals at for time positive, okay? So that's why we remove ut here, because we assume time is always positive. Okay, so if you look at this, y equals at, it's the same with using integral approach, y equals at. But it seems that using integral approach here is faster, is easier compared to using Laplace transform. So this is because the equation given here is also simple, okay? So you don't need to use Laplace transform if you have a very simple equation or simple ODE. So the purpose of Laplace transform is to solve ODE that is complex, okay? Or maybe you have more than one ODE, simultaneous ODE. So you want to solve simultaneous ODE. It's easier if you can use Laplace transform. So let's take a look at example number 2. So find the Laplace transform of f equals a times e power of minus at times ut. Okay, so this is the equation. So if you use the table, first we convert this function first, this section. So ft, if ft equals e power of negative at ut, then the frequency domain becomes 1 over s plus a. And to consider the value a here, we use linearity theorem. So you just multiply by a. So therefore, ft equals ae minus at ut. So in frequency domain, it becomes a divided by s plus a. Okay, so here in this case, if you use integration, it will take a long time to get a over s plus a. Okay, so we look at another example, example number 3. So let's say f equals 6 times e power of minus 5t plus e3t plus 5t cubed minus 9. So we have 4 different functions added together. So we use the theorem that I explained in the table, the linearity theorem. So you need to convert each of these separately, okay? And then add them together. Okay, so firstly, we convert this part first. So this becomes 1 over s plus 5, okay? Or s minus 5. It's the same as s plus 5. And then you multiply with the coefficient 6, okay? And then plus, you do the Laplace transform of the second function. Okay, so this is positive, then it becomes negative 1 over s minus 3. And then plus the third function. So here you have t power of 3. So you need to use the factorial formula. So 3 factorial divided by s power of 3 plus 1 times 5. And then minus 9. So 9 is a number. Similar to the example previously, if you have a, only a number. So it becomes 9 times 1 over s. And then simplify everything. So you get this final answer. Okay, so you don't need to simplify this into one function. Okay, I think this is acceptable already if there is a question on Laplace transform. Okay, let's look at one more example. So let's say if you have a function g equals 4 cosine 4t minus 9 sine 4t plus 2 cosine 10t. So you need to use the table and look at the cosine and sine formula. Okay, so for cosine, you simply take the number 4 here and put it in the bracket square. Okay, so the formula is s over s squared plus omega squared. Okay, so for cosine. So for sine, it becomes omega over s squared plus omega squared. Okay, so you only need to look at the coefficient of the time and then substitute into the equation given in the table. So the second function becomes negative 9, 4 over s squared plus 4 squared. And the last one, 2 times s over s squared plus 10 squared. And then simplify, you get the final answer. Okay, any question before we move on to the next subtopic?
No.
Okay, okay, so I want you to um, somehow remember this 2, 3, and 4. The definition 2, 3, and 4. So these three are very, very seldom used. And in the theorem, the definition 2 and 3. And also the differentiation theorem. So these three are commonly used. Okay? Okay, that's about Laplace transform. So we move on into using partial fraction expansion. So partial fraction is a technique that is used to separate a function in the form of fraction. So to separate a fraction or pecahan into several smaller fractions. Let's say if we have 1 over s plus a, for example. So we want to convert it into, let's say, a s plus b. Okay, ni example tak betul. So s plus c, let's say c s plus d, for example. So you want to separate this fraction into smaller fractions, okay? So the purpose of partial fraction in automatic control is to enable the use of inverse Laplace transform. So later we will see how this comes together with Laplace transform, how it is used to solve something. Okay? So partial fraction, I think you have learned in matrix, maybe in STPM, in diploma, or in calculus. So there are three cases. Generally, there are three cases for partial fraction expansion. So you need to look at the denominator or pembawah dia, okay? Pembawah of a fraction. So this is the fraction. So you need to look at the denominator, okay? Pembawah atau pembahagi. So if the roots means that, so here s plus a, so s equals minus a are the roots of this denominator. Real and distinct, maksudnya real values, and distinct, berbeza, real and different. And the second case is when the denominator, the roots are real and repeated. And the third case is when the denominator has roots of complex number. Okay. So if you go back to calculus, you can solve this manually. But in this course, we are going to look at the first example only, because this is we will use this quite common, okay, in this course, throughout this course. But the other two definition here, the other two cases here, we never asked in exam, and you can use like calculator, online calculator like MATLAB or Symbol Lab, okay. So let's look at how to apply partial fraction expansion. Okay, so the idea of partial fraction is that let's say if you have a function f equals 2 divided by s plus 1 times s plus 2. So we want to separate this fraction into smaller fractions. So we can separate this into f equals k1 over s plus 1 plus k2 over s plus 2. So basically we separate or split this fraction into two smaller fractions. And then we apply inverse Laplace transform. So the purpose of partial fraction, we want to apply inverse Laplace transform so that we get the time domain function. So from frequency domain, we get time domain function. So you will get k1 e minus t plus k2 e minus 2t. So our task on using partial fraction is to find the value of this k1 and k2. So we can use partial fraction expansion. The technique, we can use that to find k1 and k2. And then we can find the time domain function, ft. Okay, so let's say for case number 1, let's say you have y in frequency domain equals s plus 2 divided by s times s plus 5. So you want to split this fraction into smaller fraction. So you can split this fraction into a over s plus b over s plus 5. So the first thing that you need to do is you need to factorize the denominator. So let's say if your question initially given as s plus 2 divided by s squared plus 5s. So you need to factorize the denominator first. S plus 2 s times s plus 5. After you factorize, then you can split them into two fractions. The first fraction is a over s plus the second fraction b over s plus 5. Okay, now we can use partial fraction expansion technique to find a and b. So in this lecture, we use a slightly different method. So we use this method, okay? So we assume s equals 0. Then you get a equals 2 over 5. And then we assume s equals minus 5. Then we get b equals 3 over 5. Okay, so if you understand this technique, it's okay. Okay, if you don't understand, there are another technique or another method I think that you already learned in calculus. So what you can do is you simplify this fraction first. So you get a times s plus 5 plus b times s divided by s plus 5. Okay, so when you simplify this fraction, then you can equate, okay, the numerator with the original numerator. So you get a times s plus 5 plus bs equals s plus 2. And then to find a, we assume that s equals 0, so that we eliminate this part here, b times s. So when s equals 0, you get a times 0 plus 5, you get 5, equals 0 plus 2, you got 2. So here you get a equals 2 over 5. And then to find b, you assume this term equals 0. So to make sure that this term equals 0, then you take s equals minus 5. Okay, so when s equals minus 5, then you get this equals 0. Okay, so when s equals minus 5, you get negative 5b equals minus 5 plus 2, you get minus 3. So you get b equals 3 over 5. Okay, same answer, but the method shown in the slide is macam intuitive sikit, okay? Untuk orang yang cepat fikir, dia boleh guna method ni. Yang macam slow, you can do it one by one, okay? Whichever method you use, as long as you get the correct answer, it's fine, okay? So now you get A and B. Then we substitute back into the original equation here. Okay, so y equals 2 over 5 over s plus 3 over 5 over s plus 5. And then this is in frequency domain. So we want to use, we want to find the time domain function. So we use inverse Laplace transform. So we apply inverse Laplace transform. We get yt equals, okay, so this part, if we use inverse Laplace transform, so we get 2/5. Okay, so we get 2/5. And then this part here, 3/5, 1/s plus 5. So we get 3/5 e power of 5t. Okay, so we get this. Okay, so the idea of partial fraction is that we want to find the time function of this frequency function. So if we don't use partial fraction, we cannot find we cannot use inverse Laplace transform on this original function. Okay, tak boleh. So we have to perform partial fraction so that we can get the time domain function. Okay, so for the other two cases, you can use MATLAB or Symbol Lab. Okay. Okay, any question before we move on to the next subtopic?
No, sir.
Okay. I think later in tutorial, there's a question similar to this. You can try, okay, by yourself. Okay, so we have learned about Laplace transform and also partial fraction expansion. So these two techniques, we will use it to find the time domain function, from frequency function. Okay, in control system, usually we want to evaluate the behavior of a system as it change with time. Okay, so usually we will evaluate the system in time function. But to evaluate a system, the equations in time function, it's not straightforward. You need to convert it into frequency function first, and then reconvert or reverse the process and convert that into time function, because it's not easy to convert straight away from time function to time function. Okay, so you need to use another process, convert into frequency function, and then convert back to time function. So that's why we use Laplace transform and partial fraction expansion. So before we move on into before we go on into detail about modeling a system for control, we need to understand a concept, one concept. So this concept is known as transfer function. So transfer function is a frequency domain. So transfer function is in frequency domain model, okay, mathematical model that separates the input from the output. So let's say if you have an ODE, let's say dc over dt plus 2c equals r. So this is equation or model in time function. So in this equation, you cannot separate, you cannot see the separation between the input and output. So let's say the input is R input, and then the output is C is the output. So we cannot see the separation between the output and input, because here output is also in the form of differentiation, but output here is single here without any function, okay, without any differentiation. But we cannot separate them algebraically, okay. So we need to convert into frequency domain. So we convert into frequency domain, and then we can rearrange them to separate them, okay. So here, it's already separated. C is the output, and R is the input. So now we can separate them. Output over input equals some equations. So this separation here, output over input, is known as the transfer function. Okay, so this is transfer function, that an equation or a model that separates the input from the output. Okay, so when you separate the input from output, then you can perform inverse Laplace transform to get the time domain function. Okay, so basically what we want here, we want to find CT, but because this is difficult to find, we convert into frequency domain using Laplace transform, and then use partial fraction, and then use inverse Laplace transform to get YT. Okay, so this is the idea of transfer function. So let's look at how to apply this in an example. Okay, so the example just now, the equation is kind of straightforward, okay? Kind of simple. So let's say if you have an ODE, there are so many differentiations, okay? Like differentiation about C, differentiation with respect to R, and then power of 3, power of 2, so many, okay? Kalau nak guna manual integration, Einstein pun tak boleh buat pakai manual. So we use conversion, okay? We convert this equation into frequency domain. Okay, so we use Laplace transform. Okay, Laplace transform L. So we Laplace transform each of this function. So d cubed C over dt cubed, you get S cubed times big C. 3d squared C over dt squared, you get 3s squared times big C. And then 7 dc dt, you get 7s C. And then 5c, you get 5 big C equals. Now we move on to the function R. So dr squared over dt squared. So you get s squared times R, big R. For dr dt, you get 4s big R plus 3r, you get 3 big R. Now it's in a simpler form, okay? In algebraic form. So you can rearrange this. So the left-hand side here, left side, you factorize all the C, the big C. So CS, factorize. So you get S cubed plus 3S squared plus 7S plus 5 equals. So this right-hand side here, you factorize R, big R. So you get RS times S squared plus 4S plus 3. Now we want to find the transfer function. So transfer function, just now it's output over input, okay? Output over input. So usually C is output. In exam, it will tell you which one is output, which one is input, okay? So usually C is output and R is input. So we separate them. We want to find transfer function, output over input. So C over R. And then we bring R over to the left side and bring this polynomial or equation here to the right side. So you get this transfer function. Okay, so C over R equals this equation is the transfer function. Okay, so transfer function or TF. Okay, TF. Okay, so from this transfer function, you can use partial fraction expansion and then use inverse Laplace transform to get in time domain. You can also do the reverse process. Okay, you want to find the ODE from transfer function. So let's say if you have a transfer function g equals 2s plus 1 over s squared plus 6s plus 2, and this is equals c over r. Okay, c is again output and r input. Okay, so you want to do the reverse process to find the ODE from transfer function. So the first step you need to do is you cross multiply. So this multiply here and r multiply here. So you cross multiply. And then you expand c times s squared plus c times 6s plus 2 times cs equals r times 2s plus rs. And then you use inverse Laplace transform. Okay, this one you use inverse Laplace transform. So you refer to the table. So cs squared basically equals d squared c over dt squared. C times 6s equals equals 6 times dc over dt. 2 times cs equals 2 times ct equals r times 2s is 2 times dr dt and plus r if you convert you get rt. Okay, so this is in the form of ODE. Rabida. Okay, so that's how you convert from ODE to transfer function, and then the reverse process from transfer function to ODE. Okay, so that's it for today's lecture. Any question that you want to ask that maybe you are confused ataupun laju sangat ke? Okay, you can stop me anytime, okay, for next lecture. If you have question in the middle of my lectures, you just stop me, okay? Any question?
Doctor,
Yes.
so may I know the application of this domain function? Why we are finding that one? Any real application in our life?
Yes. Later on, maybe in lecture, I think lecture 3, starting lecture 3, okay, you will see the application of why we use time function, why we use frequency function. Basically, if we want to look at the application, like if we want to understand the real application, we need to go through a lot of chapters. I mean, a lot of subtopics. For example, like in frequency domain, we have a plot that we can evaluate the system stability by using frequencies. In Monday's lecture, in last lecture, I've shown to you a time function that that I say, let's say this is the value that you want, desired value, but your actual output maybe have some overshoot. Okay, so this is this you can evaluate from time function. But sometimes a system, if you want to find the time function, it's kind of messy. The process is messy, or the process requires a lot of steps, which for mathematicians, they find it very macam malas nak buat. Can we use another way that is simpler, or macam tak perlu buat time function because the equation is too complicated, for example. So we can use a plot in the form of time function, frequency. I think we are not going to learn about this plot because it's not really used much in theory. I mean, for students, but in real life, there are many applications. We call it bot plot. So bot plot is basically the same function, but it's plot against frequency. So maybe the graph maybe looks different lah, macam ni kot. Something like this. Or lebih kurang lah, I'm not sure. Okay. Maybe you can determine the system like stability, like this case. It's stable, but it takes some time to reach the stable state, okay? Steady state. But from the frequency plot, maybe you can find, you can determine the stability maybe by looking at the intersection ke, or maybe the height here ke. Okay, example. There are also another plot that you are going to learn later in chapter 4 that is more convenient to use to evaluate the system stability. Okay, so basically it's about the purpose of frequency domain is about to evaluate the system stability. Okay, because to find the time function, it's troublesome or maybe difficult. So we use frequency function instead. Okay, because it's easier, it's faster. You can use Laplace transform. So that's where the transfer function comes in. Okay. Maybe in the first 2, 3, 4 lectures, maybe you find it a bit like macam no purpose of learning this. Okay, macam, oh, why are we going to learn this? But this is like still an introduction, sort of like introduction. And starting maybe lecture 3B or something, we are going to look at some applications. Okay. Panjang pula bel ni. Okay, so I want you to try like tutorial number 2. Okay. In tutorial number 2, you will see how to use Laplace transform to convert an ODE to transfer function. And then from there, you have to use partial fraction and then inverse Laplace transform to get the time function. Okay, so you can try tutorial number 2 and also try tutorial number 1 as well that we have learned on Monday. And maybe next Monday, we will discuss this tutorial. And then the next Wednesday, we will learn on modeling a mechanical system. Okay, and another thing that you need to be reminded this lecture, Laplace transform, you will use a lot later in subsequent lectures. So please make sure you understand how to convert from time function to frequency function. And then how to convert ODE into transfer function, and then doing the reverse process. Because later on, maybe in lecture 3, lecture 2B, and so on, when I show you some example, I might skip the process, like let's say d squared dt, d squared f dt. Then I straight away convert into s squared. And then you might confuse why suddenly you get s squared f. Where does it come from? So you need to know the basics of Laplace transform. Okay. Okay. Any question before we end this lecture? Okay, so if you don't have any question, then see you again next week on Monday, and we will discuss tutorials 1 and 2. Okay.